Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. With this video, we are going to solve a problem. The problem is based on the operating principles of microwave bipolar transistors. Up till now, in the chapter of microwave transistors and tunnel diode, we started the introduction to how exactly the bipolar transistors can be operated for the microwave applications. We have also gone through what exactly the physical structures they have, the different configurations they have. Now, from the previous video, whatever the operating principles we have covered, let us solve a problem. So here we are provided with the problem statement. The problem statement is a silicon NPN transistor at 300 degree Kelvin has the following parameters. The parameters are shown by the symbolic notations. Here we have W is equal to 10 raised to the power minus 5 centimeters. Capital L suffix capital E is equal to 10 raised to the power minus 4 centimeters. Capital L suffix C is equal to 5 into 10 raised to the power minus 4 centimeters. So these are the measurements of lengths. Next to that, we have here rho suffix B. It is equal to 0.15 ohm centimeter. Rho suffix E is equal to 0.006 ohm centimeter. Rho suffix C is equal to 16 ohm centimeter. Next to that, we have capital V suffix capital E is equal to 0.5 volts. V suffix C is equal to 0.6 volts. And capital A is given as 2 into 10 raised to the power minus 2 centimeter square. Now we are asked to find in the part A the impurity densities in the emitter, base and collector regions. In the part B, the mobilities in the emitter, base and collector regions. In part C, the diffusion lengths in the emitter, base and collector regions. The part D asks us to compute the equilibrium densities in the emitter, base and correspondingly the collector regions. And at last, in the part E, we require the value of the terminal currents here. Now, if we get back to the problem statement, it is very clear that the silicon semiconductor material is used in the manufacturing of the bipolar transistor here, and the transistor configuration simply has the semiconductor materials into the sequence NPN. So it means that N type of emitter, P type of base and again N type of collector region we have with these given details. So very first of all, from the problem statement, whatever the symbolic notations we have, we shall be identifying what are the given details, and then we shall be proceeding to find the solutions for part A through part E. So very first of all, in the problem statement, the first parameter that has been denoted by W, we start with, so this is the given data. So W denotes here the base width. So base width is provided to we people, that is 10 raised to power minus 5 centimeters. After W, we have the next parameter. The next parameter is denoted as capital L suffix capital E. It is nothing but the diffusion length. Diffusion length in the emitter, hence the suffix is capital E. So we have the diffusion length into the emitter by the value that it is 10 raised to the power minus 4 centimeters. Similarly, the next parameter is also the diffusion length, and this diffusion length is for the region collector. The corresponding value here we have 5 into 10 raised to the power minus 4 centimeter. From the given details, it is very clear that as far as the dimensions of these three regions are concerned, the collector has largest dimension as compared to the emitter here and then to the base also. So this is the base width. These are the lengths with respect to emitter and collector, the first three parameters. Next to that, here we have the values of resistivities. So we have, very first of all, the base resistivity mentioned into the ohm centimeter. So this is represented as rho suffix b, and the value is provided to us that it is 0.15 centimeter. Similarly, the next parameter is for resistivity of emitter region. So emitter resistivity here we have, and the value we have 0.006 ohm centimeter. After that, we have the resistivity for collector, and the value it is, we have 16 ohm centimeter. Now we have only the last three parameters to be identified. So here we start with V suffix E. So V suffix E in the problem statement is nothing but the voltage with respect to the emitter junction. Hence I mention here it is emitter junction voltage. The value provided is 0.5 volts. Whereas next to that we have the collector junction voltage. The collector junction voltage Vc is with the value 0.6 volts. And now capital A, the unit, if you see, it is nothing but the cross-sectional area. So cross-sectional area capital A is equal to 2 into 10 raised to the power minus 2 centimeter squares. Now we get back to the problem statement. So now all the given details, 9 parameters we have identified. Now we require the value of the impurity densities in the emitter, base and collector regions. Now for finding the impurity densities out of these 9 parameters, which parameter will be helpful and which parameters will be redundant, that we need to see. So here whatever the resistivities with respect to the base, emitter and the collector, here we have, those will be helpful to us. So for that purpose we get back to a graph representation of finding the impurity densities versus the resistivity values. So here in this graph, onto the horizontal axis we have the impurity concentrations. Impurity concentration or impurity densities we can call, and it is a measure in terms of per centimeter cube here. So here we have the markings right from 10 raised to power 12 to that of 10 raised to power 21. So these many number of charge carriers may be present there. So this is with respect to the resistivity value of the semiconductor material, which is different for the base, emitter and that of the collector region. So on the vertical axis we have the resistivities in terms of ohm centimeter. So in the problem statement we have the values of resistivities and we need to find the values of impurity concentrations. Now here in this particular graph, the different materials are gallium arsenide and that of the silicon. So here we have p-type gallium arsenide with a dashed line here, p-type silicon with a solid line, then we have n-type gallium arsenide with a dashed line and n-type silicon with a solid line. So if we mark the resistivity values onto the vertical axis, we can be able to find the corresponding impurity concentrations on the horizontal axis. So here these values are applicable when the temperature is at 300 degree Kelvin. So using this graph we find the answer for the part A. So in the part A I mention the impurity densities or impurity concentration. Very first of all for the emitter, so I mention impurity density and D, also give the suffix capital E for emitter. The value we find from the graph that it is 1 into 10 raised to the power 19 per centimeter cube here. So this is for the N type of the emitter region. Next to that, we require the impurity density with respect to the base, that can be denoted as N suffix D, capital B for the base here. So from the graph we get the value that it is 1.5 into 10 raised to power 17 per centimeter cube. Now this is for the P type of the material of base here. Now the last region, that it is the collector, so impurity density is denoted as capital N suffix DC, and the value can be obtained as 3 into 10 raised to power 14 per centimeter cube here. So this value is for N type. So first one for N, then P, and then N. So as per the problem statement, NPN bipolar transistor we have here. So this is the solution for part A. Now after finding the answer for part A, we require in the part B to be computed the mobilities into the corresponding emitter, base and collector regions here. So for finding the mobilities, we take the help of another kind of graph. So in this graph, onto the horizontal axis we have impurity concentrations again in terms of per centimeter cube, and onto the vertical axis we have the mobilities here. So whatever the answers we have found from the previous graph, and as the answer of part A will be used as inputs here, and then the answer for part B can be computed here. Now we have three different graphs corresponding to three different semiconductor materials. Those are germanium at 300 degree kelvins, silicon again at 300 degree kelvins, and then gallium arsenide again for 300 degree kelvins. In each of the graph we find two solid lines, one for the N type, another for the P type here. So as our problem statement tells us that it is for silicon material, we shall be confined to the middle graph here. So mu N denotes the mobility of the electrons, whereas mu P denotes mobility of the holes here. So from the problem statement we get back to the answer for part B here. So here for part B we find for the emitter region that the mobility of the holes, so mu suffix P suffix capital E, the value is found to be equal to 80. So here the unit of mobility as provided is centimeter square per volt second here. Next to that, the next mobility can be in the emitter again, so it will be mu suffix N along with capital E. That value is found to be 105 again in terms of centimeter square per volt second. The next one is for the base region, so it will be mu suffix P capital B. The value is determined that it is 400 centimeter square per volt second. And next to that, the last value can be for the collector, so it will be mu suffix N capital C, the representation, and the value is 1600 centimeter square per volt second. So this is the answer for part B. So we get back to the problem. After solving the answer for part B, in the part C we require the value of diffusion lengths in the corresponding emitter, base and collector regions here. So for determination of the diffusion lengths for part C, we start with the use of formulae. So in the part C, we have the diffusion lengths represented with the help of the coefficients capital D suffix capital E for emitter and P for the P type here we shall be, or for the holes here it will be. So it is simply the multiplication of the mobilities that we have determined into the previous part. So mu suffix PE into capital V suffix T. So the voltage with respect to the temperature, So that voltage is to be multiplied with these particular mobility values. So we get the calculation 80 into 26 into 10 raised to the power minus 3, the value of Vt here that we have substituted. So this brings us the answer that it is 2.08. Now for this representation of diffusion length by capital D suffix Pe, we have the unit that it is centimeter square per second here. Similarly, the second type of the diffusion length can be represented into the emitter, that it is capital D suffix Ne here. So it will be the simply multiplication of mu suffix Ne into Vt. So here we multiply 105 with the same value 26 into 10 raised to the power minus 3, and this gives us the result that it is 2.73 centimeter square per second. For the base region, the diffusion length can be denoted with the help of the coefficient that it is capital D suffix Pb here, a multiplication of mu suffix Pb into Vt. So it will be, we have 400 into 26 into 10 raised to the power minus 3. The value, it will be 10.4 in terms of centimeter square per second. And the last diffusion length coefficient value, that will be represented as capital D suffix N capital C. So it will be the multiplication of mu suffix Nc into Vt. So this is equal to, here we have 1600 as the answer from part B into 26 into 10 raised to the power minus 3. The resultant value, that it is 41.6 centimeter square per second. So these are the answers for part C here. Now after getting the answers for part C, we go for the part D here. In the part D, the equilibrium densities into the corresponding emitter, base and collector regions are to be determined here. Now the equilibrium densities corresponding to the emitter, base and collector regions are denoted here for the part D by N suffix Pb here. Then here we have P suffix EO there and P suffix CO for the base, emitter and the collector, which are computed by the use of intrinsic concentration, that it is an I square divided by the impurity concentrations or the densities that we have along with. So it will be Na into capital B representation for the base. For the emitter, here we have Ni square divided by, it will be NdB here, and it will be Ni square divided by NdC here. So here the differentiation with respect to the D and A here, it is for the acceptor and the donor type of impurities here. Now we can make the substitution of values. So in the numerator, the intrinsic concentration for the silicon material, here we have 1.5 into 10 raised to the power 10. So this is to be squared, and it is divided by the concentration of the impurity here, that it is 1.5 into 10 raised to the power 17 in the first case, giving us the answer that it is 1.5 into 10 raised to the power 3. So this is nothing but the concentration to be measured per centimeter cube here. So this is the first sub answer for part D. For the next emitter region, we substitute the values 1.5 into 10 raised to the power 10, which is to be squared, and then further it is divided by the value of 1 into 10 raised to the power 19 here we substitute. So this gives us the answer 2.5 into 10 raised to the power 4 here. So this answer is also in terms of per centimeter cube here. Next to that, we have the substitution as 1.5 into 10 raised to power 10 to be squared. So here it is divided by, we have the impurity concentration 3 into 10 raised to power 14. So this square and the division gives us the answer that it is 7.5 into 10 raised to the power 5 here. So this is also a measurement in terms of per centimeter cube here. So this way we are also covered with finding the answer for part D here. Now the last part is left. In the part E, we require the terminal current values here. So in this part, we are going to solve for 7 types of different currents in the transistor here. So we begin for part E here, and in the part E, the first type of the current, that current is for the electron current in the first region, that it is nothing but emitter region. So this current is denoted by capital I for the current, N for representation of the carrier, that it is nothing but the electron here, and for the emitter case we put capital E in the suffix here. So this is determined by, here we have a formula, capital A in multiplication to the electronic charge Q into capital D suffix N, the diffusion coefficient, into the square of the intrinsic concentration, and it is divided by the impurity concentration Na into the width W, and this all ratio is in multiplication to the exponent, that it is e to the power, here we have capital V suffix E divided by capital V suffix T. So to see the formula, we have all the values. So in the next step, we substitute the values as capital A is nothing but 2 into 10 raised to power minus 2. Electronic charge is 1.6 into 10 raised to power minus 19. Dn value we have determined. The Dn value is nothing but, for this case, 2.73 for the emitter N type here. This is in multiplication to the square of intrinsic concentration. So it is 1.5 into 10 raised to power 10 to be squared. So this is all divided by, here we have the impurity concentration substituted as 1.5 into 10 raised to power 17 in multiplication to the W, that it is 10 raised to power minus 5 we can be substituting. So this is in multiplication to the exponential of, so here we put 0.5, the value of V, divided by 26 into 10 raised to power minus 3 here. So we simplify the value, that it is minus 13.104 into 10 raised to power minus 13 into, here we have 2.248 into 10 raised to power 8 here, and the multiplication gives the final value for the current here in the emitter for the electron carriers here, that it is minus 0.2946 into 10 raised to power minus 3. So it can be represented as milliamperes here. So this is the first type of the current into the bipolar transistor. Next to that, we shall be determining into the same emitter region the current because of the another type of the charge carrier, that is nothing but the holes here. So therefore in the part E, we have second type of current denoted as capital I suffix P capital E here. So it can be given by the equation capital A Q dP Ni square divided by, here we have the multiplication of the diffusion length Le into the concentration of impurity Nd, and along with the exponential of Ve by Vt we subtract 1 from it. So this is the formula. So now we substitute the values. The numerator, it will be 2 into 10 raised to power minus 2 for A, into 1.6 into 10 raised to power minus 19 for Q, in multiplication to 2.08 into 1.5 into 10 raised to power 10, that is to be squared, and this is all divided by the multiplication of 10 raised to power minus 4 into 1 into 10 raised to power 19, the concentration of impurities here, and this is in multiplication to, here we have 2.248 into 10 raised to power 8 computed from the earlier answer of current. Here we subtract 1 from this, so this simplifies to the step of, we have 14.976 into 10 raised to power minus 16 in multiplication to 2.248 into 10 raised to power plus 8. So this gives us the answer 0.337 into 10 raised to the power minus 6. So as this is to be written in terms of amperes, we can also get it converted to the microamperes. So the answer for capital I suffix PE is equal to 0.337 microampere. So this is the another terminal current here we have in the given bipolar transistor. Now the third type of the current is for the collector region. So I mention here, and this current is nothing but the reverse saturation current, and this is in the collector, hence I represent it by capital I suffix CO. So it is computed by the use of formula minus A into Q into dN and I square divided by the impurity concentration into W here. So substituting the values, minus, here we have again the second term, that is A into Q into the diffusion coefficient dP here, in multiplication to, here we have P suffix N0. So this is divided by L suffix capital E. Now we have all the values. When we substitute them, we get two terms that are simplified to the values minus 13.104 into 10 raised to power minus 13, and the second term is minus 14.976 into 10 raised to power minus 16 here. So this gives us the answer minus 1.312 into 10 raised to power minus 12, that can be written as pico in terms of amperes here. So this is the third current we have determined. Now the next current we represent as the fourth current, and we denote it for the collector region, and it is because of the electrons, hence we represent it as capital I suffix NC. So it is given by minus capital A into Q into dN into Ni square divided by the impurity concentration into W in multiplication to the exponential e to the power V by Vt here. Substituting the values, we get the simplified form, that is minus 13.104 into 10 raised to power minus 13 into 2.248 in multiplication to 10 raised to power 8 here. So this gives the answer minus 0.2946 into 10 raised to power minus 3, hence I write milliamperes here. So this is the INC, the third type, the fourth type of the current here. Next to that, we have the fifth current. The fifth current is for the emitter region. The total emitter region current we can be denoting by capital I suffix capital E here. So it will be the addition of minus IPE we have computed before, plus capital I suffix NE here. The two values we put here, so it will be minus 33.67 into 10 raised to power minus 8, and this will be minus 0.295 into 10 raised to power minus 3 here. So this gives the answer minus 0.295 into 10 raised to the power minus 3 here. So we put it minus 0.295 milliamperes as the answer for emitter current IE. The sixth value is now for the collector region. So I mentioned here for the collector current capital I suffix C. So it is nothing but the computed values of minus of ICO minus of INC here. So this will be 1.312, as it is minus, the magnitude we have determined to be minus, it will be getting to the plus here. In multiplication to 10 raised to power minus 12 here, minus, again we have minus value 0.295 into 10 raised to power minus 3. So gives us the answer positive value of 0.295 milliamperes we can take it for. Next to that we have the seventh current. The seventh current is for the base terminal denoted by capital I suffix B, and it will be computed by the use of I suffix PE minus in the bracket I suffix NE minus of INC plus ICO. So we substitute the values. It is 33.67 into 10 raised to power minus 8 minus of minus 29.46 into 10 raised to power minus 5, added with we have 29.46 into 10 raised to power minus 5, and the last term is added 1.312 into 10 raised to power minus 12. This gives the added output of the current here for the base here, that it is 0.337 into 10 raised to power minus 6, that we can write it to be the micro amperes here. So this is the answer. So here we are covered with all the answers for part A through part E for operating principles of microwave bipolar transistors. By the next lecture, we shall be addressing the amplification phenomena for microwave bipolar transistors. I hope you enjoy the knowledge we share for the subject microwave engineering. For more information like this, you can subscribe to Ekeeda channel. Thank you.